Hi everybody, welcome back. Today we're going to be talking about quantum simulation. Now, quantum simulation, it's actually probably one of the most useful applications that have been developed so far for quantum computing. The primary purpose of quantum simulation is to be able to basically enact the unitary dynamics predicted by the solution to the Schrodinger equation. So in this way, we can simulate chemistry, physics, all sorts of dynamics on a quantum computer in polynomial time, whereas the best known exact classical methods for solving these problems run in exponential time. So this is a very important aspect of quantum computing, even if you actually don't care about simulating physics directly by itself. The reason why is because of the fact that quantum simulation ends up being a subroutine that's used in other quantum algorithms, such as quantum linear systems algorithms, quantum algorithms for solving differential equations, quantum algorithms for solving semi-definite programs, and the list actually goes on. So the point is that it's really important to be able to understand this, because the techniques that we end up using for this are used for those practical applications, but they're also used for theoretical applications. Because we're often, when we ask about if we're interested in asking what the computational power of physical systems are, there's two sides of this. What we'd ideally like to be able to do is determine first, can that particular system implement a quantum computer, i.e. can it simulate any quantum computational device that's realistic in polynomial time? Or, on the other hand, is it possible that a quantum computer can simulate? Those two questions really give us a lot of qualitative understanding for how complex a particular quantum system is. So that's one of the reasons theoretically why we're interested in that. But let me start from the beginning. I'm going to be taking a perspective here that none of you have seen quantum mechanics itself before, but actually it's surprisingly straightforward, especially having worked with quantum theory for as long as you have through this course. So I'm going to begin by with the Schrodinger equation. Okay, so the Schrodinger equation. There's many different representations for the Schrodinger equation. The version that I'm going to be giving you is actually more general than the standard representation that you might have seen in a differential equations course. The equation of motion for a quantum state, according to the Schrodinger equation, can be written in the following form. Now, let's imagine that psi of t, this over here, can be thought of as a function. Psi of t can be thought of as a function that ends up mapping a real parameter, time, to a quantum state vector, c2 to the n. Okay? And the equation of motion for this function, which we just think of as a time-dependent quantum state, is the derivative of that state with respect to time is equal to negative iht. Now, we can end up writing psi of t, formally speaking, we'll just express that to be some operator. I'm going to call this operator u of t that acts on an initial state, psi of 0. And, excuse me, this operator is often called the time evolution operator. Okay, and what it does is it does exactly what it sounds like. It takes an initial quantum state and evolves it in time to some later quantum state. All right, and if we make this substitution, sorry, I miswrote the Schrodinger equation, IH psi of t. Okay, if we substitute this expression in here, what we end up with is we end up getting the following matrix differential equation. We end up getting du of t dt is equal to negative IH u of t. And the solution to this operator differential equation, turns out, is e to the minus IHT. Now, to give you an idea about what this h is, which I should have said immediately, this is an operator or matrix known as a Hamiltonian. So when you hear about Hamiltonian simulation, this is what they mean. We actually, unfortunately, when we say Hamiltonian simulation, we don't actually mean simulating the action of this Hamiltonian matrix. We mean implementing this matrix u of t over here. Okay? Now the Hamiltonian, you might ask, well, what is it? Well, the Hamiltonian, this is the energy operator. In essence. So what it ends up giving us is that if we, for any quantum state, compute the average value of this, this is defined to be the mean energy of the quantum state. So that's the notion of the Hamiltonian. Really, just think about it as like a matrix version of the energy. Okay? So what we would like to be able to do is, our task is to figure out whether or not we can build this time evolution operator on a quantum computer. Because if we can build u of t equals e to the minus IHT, then what we can do is we can do the following. We can start from some particular state and evolve in time. So my first claim I'm going to make is claim if h is equal to h dagger, which is typically what we're going to assume in most cases. This is known as a Hermitian matrix. Then u of t is unitary. Okay, there's a number of ways that we can prove this, but here's the easiest way. So if we take a look at e to the minus IHT, e to the IHT, this is unitary if that is equal to 1 and e to the IHT equals e to the minus IHT conjugate transpose. Now this latter fact actually is true under the assumption that h is Hermitian. We can see this by expressing the time evolution operator as a Taylor series. Okay? Now, what we do is, if we want to be able to figure out what the conjugate transpose of this is, we can just take the conjugate transpose of both sides. But because the conjugate transpose of the sum is the sum of the conjugate transpose, this is equal to j equals 0 to infinity, negative IHT to the j conjugate transpose over j factorial. Great. So now, if we take a look at what happens when we expand this all out, basically what ends up happening is it maps all the i's to minus I when we take the conjugate transpose of this product. This ends up becoming the sum from j equals 0 to infinity of IHT to the j over j factorial, which, grouping this back together using a Taylor series definition, this is equal to e to the IHT. So therefore, we've demonstrated this fact. The next thing we've got to do is demonstrate that fact as a consequence of this. So now, the first question is, all right, we'd like to be able to show that e to the minus IHT, e to the IHT equals identity. That's going to be a little bit difficult. So instead of doing that, what I'm going to do is I'm going to ask, what's the derivative of e to the minus IHT, e to the IHT? Well, that is equal to, using the product rule, this is e to the negative IHT times IHT, or IH, e to the IHT, plus negative IH, e to the minus IHT, you get to the IHT. But by Taylor expanding this, we can end up seeing that this is actually equal to IH minus IH e to the negative IHT e to the IHT over here. Another way of wording this is that because H commutes with e to the minus IHT, i.e. e to the minus IHT H is equal to H e to the minus IHT, then this result follows. This wouldn't be true, of course, for generic matrices. So these two terms cancel, and therefore the derivative is 0. So whatever this object is as a function of t, it's a constant. So if we want to be able to figure out what its value is, all we have to do is evaluate it at the easiest possible point. So the easiest possible point that we can evaluate it at is t equals 0. So if we substitute in t equals 0, this is just identity times identity equals identity. And this ends up proving our claim because it's unitary if and only if that property is true. So therefore, e to the negative IHT is a unitary. And therefore, a quantum computer can approximate it within error epsilon for all epsilon greater than 0. All right. So to give you an idea about, at a high level, how the quantum simulation protocol works, is the easiest way to think about it is to think about it in two different spaces. Okay, this is the vector space for the quantum system. This over here is going to be our quantum computer vector space. Now, in general, I'm going to draw this vector space being bigger. In some cases, they'll be precisely the same size. But what we do is we have an initial state, psi of 0, inside our physical system, and it's evolving smoothly in time to some final state, psi of t, using some dynamics over here, which is given by e to the minus IHT. The way that we perform a simulation is that first we perform an embedding of this problem within a subspace of our higher dimensional Hilbert space. This embedding maps the state to some equivalent one, I'll call it psi tilde of 0. Next, what we want to do is we want to implement e to the minus IHT. But instead of this being a smooth evolution, now we're going to be moving all over the place using a bunch of jagged discrete gates to some final state over here. I'll call that state psi tilde of t. What we would like to do is we'd like this state under our mapping that connects the two states. We'd like this one to map back to another state within distance epsilon. So that's the notion of simulation. We've got to really think about two sorts of worlds. One, the world of the system we're trying to simulate, and one is the world of the computer doing the simulation. Most of our time isn't going to be spent on this encoding or this decoding step. To some extent, the physicist or the problem itself will tell you the natural way of doing it. The part that is hardest and most general is this translation step where we're getting the smooth dynamics in the world of the simulator and mapping that over to the discrete dynamics that we see here in the quantum computer. So that's what we're going to be spending most of our time doing. And so to begin with, let's look at this process through the lens of computer science. If we look at it through the lens of computer science, this is really just a compilation problem for an arbitrary unitary. So what we'd like to do is we'd like to be able to find ways of mapping these unitaries into gate operations. And ideally, we'd like to be able to do this without exponential overheads like we would normally have if we were performing this on a using the techniques that we saw early in the course. So to do this, let me begin with the easiest possible Hamiltonian that we could simulate. Recall that a Hamiltonian is a Hermitian matrix. And actually, in general, we can always end up writing this Hermitian matrix as a sum over AJ, PJ over here, where each of these is a Pauli operator. In fact, we can always end up finding AJ using that formula that I mentioned before. We can find this by taking 1 over the dimension of the matrix trace of PJ against H. So in general, if we just have some arbitrary Hermitian matrix, we can always find what these coefficients are by using this matrix inner product here. But in any case, let's just assume that a bunch of smart physicists end up giving us a sequence of AJs that they care about. Okay? Now, recall, by Pauli operators, what I mean over here is I mean a series of operators taken from the alphabet, tensored n times. Okay? So for example, using this language, Z tensor Z is a Pauli operator. I tensor Z is a Pauli operator. X tensor Y tensor Z, that's a Pauli operator as well. Okay, so this is it. So let's take a look at the simplest one we can view. Let's look at H equals Pauli Z. Then in that case, this physically might model a system that has magnetic field pointing along the Z direction. But in any case, the time evolution operator that we need to compile to solve this problem is e to the minus IHT, which is e to the minus I ZT. Now, before we continue, I guess what I should do is I should make some assumptions about our gates. The gates that I'm going to assume that we end up having for this discussion is I'm going to end up assuming that we have the gate RZ of theta, Hadamard, and I'm going to assume that we have C naught as well. I'm not going to need Toffoli for this, but you can obviously build Toffoli out of these gates because they're a universal gate set. So recall that RZ of theta, that is equal to e to the minus I Z theta over 2. And so we can see that in this case, e to the minus IHT is equal to e to the minus IZT is equal to RZ of 2t. So therefore, our simulation circuit for e to the minus IHT is really simple in this case. It is just going to be RZ of 2t. Okay. Now, let's look at the next simplest case. Let's say that our Hamiltonian is equal to x. Oh, by the way, one of the things that is confusing about this is that the symbol h in this literature is used for the Hadamard gate, and as well as the Hamiltonian. So one of the things that I'm going to try to do for the rest of this conversation is I'm going to try to remember to put hats only on the Hamiltonians, just for clarity. And the h's I'm going to leave as the Hadamard transformation. So in any case, if the Hamiltonian now is poly x, what we can do is we can perform this simulation using the following trick. We can note that the time evolution operator is e to the minus I x t. However, if you recall earlier in the course, there's an identity for operator exponentials. That in general, if we have e to the a u dagger for any unitary matrix U, then this is equal to e to the u a u dagger. So, using the fact that Hadamard transform x Hadamard is equal to z, we can see that Hadamard e to the negative I zt Hadamard is equal to e to the minus I xt. So what this ends up meaning is that we can construct this simulation through the following quantum circuit. Okay, this quantum circuit basically is just doing the exact same thing as the Z simulation, except we're transforming from Z to X by doing this over here. Another way of thinking about this is that these over here diagonalize e to the minus IH hat t. And so what we're doing is we're diagonalizing it to convert it into a z rotation and then solving that using the previous techniques. So, for example, now let me do one that's it's pretty easy and obvious, but let's look at the case where the Hamiltonian is now a tensor product of poly z and poly x. In this case, then the time evolution operator that we would end up getting is actually just going to be the... Oh, actually, this one's a little bit harder. My apologies. Let's save that one for later. All right, cool. So if we wanted to do Hadamard, let's say we look at the next simplest Hamiltonian, which would be of the form Z tensor Z. Okay. Then the question is, well, what's the time evolution operator? You might be tempted to say, well, time evolution operator is e to the minus I Z tensor Z t, and that's surely going to be equal to e to the minus I Z t tensor e to the minus I Z t, all right? But that is wrong. The operator exponential of the tensor product is not equal to the tensor product of the operator exponentials. We're going to have to think more about how to implement this guy right here, all right? So the way that we're going to do this is just to ask, okay, well, what is this function over here? All right, well, first thing that we can note is Z tensor Z squared is equal to the identity. In fact, actually, in general, any poly operator squared will end up giving us the identity. So if we have e to the minus I Z tensor Z t, by using Taylor's theorem, this is the sum from j equals 0 to infinity of negative I Z tensor Z to the t, or times t to the jth power over j factorial. Now, if we have this expansion over here for it, we can note that all the terms that are satisfy Z tensor that are even will give us an identity. So in general, if we have a Z tensor Z to the 2k, we'll get I, whereas Z tensor Z to the 2k plus 1 is just going to equal Z tensor Z. So what we end up getting is that this whole expansion can be written as sum of two different parts. Sum from j equals 0 to infinity of negative I to the 2j identity over 2j factorial plus the odd components, which we can write very similarly as negative I to the 2j plus 1 z tensor z over 2j plus 1 factorial. Okay, now this is unsurprisingly equal to, oh, I forgot the factors of t in here, t and t. So this is equal to cosine of t identity minus I sine of t times z tensor z. So this is an expression for what the operator is effectively. So we can see that if we have e to the negative I z tensor z acting on a state t of 0, 0, this is the same thing as cosine of t minus I sine of t acting on 0, 0. Similarly, 1, 1 maps to cosine of t minus I sine of t, 1, 1. Now, those are really boring, but the interesting ones end up coming in with the mixed terms. So when we apply this to 0, 1, we end up getting, well, the first one is just going to be cosine of t, 0, 1. But the next one is going to be negative I sine t, z, 0, tensor, z, 1. And all I've done over here is just used the fact I've explicitly written this as a tensor product. So I'm using Dirac notation. These two things are equivalent, and now I've just expanded the tensor product up on this side. So this ends up giving me cosine of t plus I sine of t acting on state 0, 1. So if we take a look at this, these over here can just be rewritten as e to the negative it, and this one can be written as e to the it. So the matrix representation for this guy over here, just so we can visualize this, is of the form e to the negative it, e to the it, e to the it, e to the minus it, and 0 everywhere else. Okay? So that is the matrix form for this. In general, actually, for a diagonal operation, we can actually just follow the exact same sort of reasoning in order to be able to say that the function, the matrix valued function is just going to be the matrix of the function values. But that wouldn't be true in general. Okay, so this is how we end up arguing about what exactly the form of the operator is. Okay, so we have this particular Hamiltonian, and there's a pattern to this. So let's just take a look at what the basis states are over here, right? So these are the states, and these are the corresponding phases that end up getting kicked back. You'll note that the phase is e to the it if and only if the parity of this is even. And what I mean by the parity is the number of ones. And in particular, if we end up getting that, let's call this A and B. So if A exclusive or B is equal to 1 then the sign gets flipped. All right, so now we can ask ourselves, how can we end up flipping a sign? So if we go back to our recollection of Pauli operators, we can use the fact that x, z is equal to minus zx. And therefore, by right multiplying both sides by x, we can see that this is equal to minus z x squared, which is equal to just minus z, because, again, x squared is just identity. So, if we want to flip the sign of z, we can do that by x rotating. Similarly, what we end up seeing then is that e to the minus I z t x x is equal to, using this unitary rule that we used extensively early in the class here, we end up finding this is the same thing as e to the negative I x z x t. So this we can end up, of course, expressing as e to the I zt. So what we'd like to do is we'd like to really be able to conditionally put those x's in. So the way that we can build this circuit is actually really straightforwardly. What we do is we do the following. Let's say we begin with a state A over here and a state B. We perform a pair of C naughts. Then the state down here will end up becoming A exclusive OR B. Another way of thinking about it is that conditioned on this top value, we are going to flip the sign. So we'll do a RZ of 2t now, and we will unflip. Now the phase that we end up getting back is we will get back, once we do, if we do the analysis, we will get back e to the minus I t negative 1 to the A exclusive OR B times A B, coming back from it, which is the exact same pattern that we see here. So therefore, what this implies is that e to the negative I z tensor z, that is equal to, times t. This can be compiled down to the circuit. RZ 2t. Great. Now, what happens, going back to the previous case that I said was too hard, what happens if we wanted to do, well, e to the minus I x tensor z t? Well, again, we can use the fact that x is equal to Hadamard z Hadamard, and therefore this is equal to e to the negative I Hadamard z Hadamard tensor z t. Okay, but using the unitary identity, this is the same thing as Hadamard tensor identity e to the minus I z tensor z t Hadamard tensor identity, which corresponds to the quantum circuit Hadamard C naught going down here, followed by an RZ of 2t C naught, and then finally a Hadamard transform. So that is how we would end up doing that. Basically, the strategy is very simple. What we do is we perform basis rotations to convert the Hamiltonian over to a Z Hamiltonian, and then we just simulate the Z Hamiltonian. All right, great. Now, one last example I'd like to show you before we start dealing with the more general case. The last example I'd like to show is the example of a three-fold tensor product. So, say we have e to the negative I, z tensor, z t is equal to e to the minus I h hat t. Okay, great. So what do we do here? Well, we can use the exact same reasoning. We can argue that e to the negative I, z tensor, z t is equal to cosine t identity minus I sine t z tensor, z, using the exact same argument I gave previously. Okay, cool. So now, let's just ask, if this is acting on a state, let's call this state P, what will happen is that, and I'll say this is equal to P0, P1, P2, then e to the negative I, z tensor, z t, acting on P, is then going to be equal to e to the negative I, or sorry, I won't skip this step, negative I times negative 1 to the P0 plus P1 plus P2 sine t, all acting on P. And all I've done here is I've just evaluated what these z's are. If P0 or P1 or P2 is equal to 1, we'll get a minus sign back from it. So I'm just counting the minus signs that I end up getting from this. Now, because of, you can see that because my negative 1 squared is equal to 1, we can see that this is exactly equal to cosine t negative I times negative 1 to the P naught exclusive or P1 exclusive or P2 sine t P, which we can always end up expressing as, using Euler's identity, as just e to the negative I, negative 1 to the P naught exclusive or P1 exclusive or P2 acting on P times t. Okay, great. So the same thing ends up happening. We're going to end up getting, if we express this out, we would get a matrix whose sign would end up going e to the negative I t over here, e to the I t, because now we've got 1. Now we're going to switch back it, and so on and so forth. Okay? So this is the particular pattern that we end up getting. Another way that we can view it is that what we want to do is we want to have a single qubit rotation, but we want the sign of that rotation to flip depending on this value. So doing the exact same trick that we did last time, we can do this by following. Where this is P0, P1, and P2. All right, and we can see that basically what ends up happening to this is this will carry out precisely the same transformation that we require. So this is equal to e to the minus I h hat t. In general, if we end up having, if h hat is equal to z tensor q, then e to the negative I z tensor q t Similarly, just by repeating the exact same reasoning, it can be implemented just by the following sequence. Okay, and this is just a generalization of the exact same pattern that we saw before. We carry out this sequence in order to find the parity of all of the individual bits. We then do a rotation and we uncompute the parity. And that's how we can simulate any poly operator. So this is a step in the right direction, but it doesn't give you everything you need in order to be able to solve these problems. A key problem is that what ends up happening if we have the sum of two such terms? So to see how we would solve this, let's take a look at the fifth case, which is e to the negative I, let's say identity tensor x plus z tensor z t. Okay, so in this case, h is equal to identity tensor x plus z tensor z. And for you physics aficionados, this would be an example of a transversizing model. Okay, so this this over here, you might be tempted to try to say, okay, well, this I can reduce this to things we already know. I can use the properties of exponentials to end up saying, well, this is just equal to e to the negative I z tensor z t, right? And actually, this is wrong in general, because of the fact that this relationship only holds when two operators commute. If they don't commute, then this is entirely wrong. So, what are we going to do? The way that we handle this is by using an approximation known as the Trotter-Suzuki approximation. And the Trotter-Suzuki approximation says that for any exponential of matrices, e to the a plus b times t, that this is equal to e to the at, e to the bt, plus terms that are of order norm a, norm b, t squared. Okay? So this ends up working in the case when that is a small quantity. So if this is small, then the Trotter-Suzuki approximation holds. However, if time is large, then this doesn't hold. All right, great. So let me justify the Trotter-Suzuki approximation to you. So, proof. Okay. The e to the a plus b t, we can always express this as identity plus a plus b t plus sum from j equals 2 to infinity a plus b t over j factorial to the j. Okay, so in order to be able to get an idea then about how large these particular terms end up getting, actually let me just say that this is, yeah, okay, I'll worry about that later. Then, if we expand this guy out, note that this ends up being an operator over here that has norm from the triangle inequality at most norm of a plus b t squared times e to the norm a plus b t. Okay, so if we end up using that, now let's assume, because we're interested in a small asymptotic expansion, I'm going to end up assuming that max norm a b t is less than or equal to, I don't know, 1, 2, say. Then this whole thing is clearly then going to be in order, and this maximum quantity I'll call lambda. This is going to be in the order of lambda squared t squared. So that's how big this remainder term is. Now, let's take a look at e to the at, e to the bt. Using Taylor's theorem, again, we can express this as identity plus at plus sum j equals 2 to infinity of at to the j over j factorial multiplied through by the exact same thing but with b, plus sum j equals 2 to infinity bt to the j over j factorial. All right. And now, so we do exactly the same thing. This is equal to identity plus a plus b times t plus an additional operator that is going to be of norm at most norm of identity plus a t times the norm of sum j equals 2 to infinity of a t to the j over j factorial plus the same thing for b. And this here, what I'm trying to say is I'm trying to say that this bit is the magnitude of the whatever operator we get or matrix that we get from the rest of these terms. Okay, so if that's the case, then we can end up seeing clearly that under our assumptions, this is also order lambda squared t squared, just by expanding this out and grouping all of the terms and noting that this is less than or equal to 1. Or more accurately, I guess, this is in order 1. So it doesn't actually end up changing the asymptotics. So therefore, what we end up getting is we end up getting from the Taylor series expansion, we end up getting that e to the at, e to the bt minus e to the a plus b t is in order lambda squared t squared. Okay, where again this lambda parameter is equal to the maximum matrix norm of A and matrix norm of B. So in general, the matrix norm over here, this is just defined to be the maximum eigenvalue of A. Okay, so that is how you can justify the Trotter-Suzuki formula. So what this ends up saying is, for our particular case, is that what we have is that e to the negative I x tensor identity t plus z tensor zt. This is equal to e to the negative I x tensor identity t e to the negative I z tensor z t plus terms that are, in this case, order t squared. All right. Now, this is great if this is small, but if t isn't small, then this error could be enormous. So how are we going to do this? What we're going to do is we're going to take the case where we have a big evolution time t, and we're going to break it up into a series of time slices. We're going to break it up into r little bits. And then what we're going to do is we're going to say, well, e to the negative I x tensor identity t plus z tensor z t, that is equal to e to the negative I x tensor identity plus z tensor z t divided by r, all raised to the rth power. So what I'm saying is take a small little step of duration t over r and repeat that r times. That the total time that we get by repeating each of these short time steps, this guy, is exactly the same. But it turns out, even though this is equivalent for the exact evolution, it's not quite the same for the approximate evolution. For the approximate evolution, we end up getting that e to the negative I x tensor identity t over r, let's just look at the norm of this, times e to the negative I z tensor z t over r minus e to the negative I x tensor identity plus z tensor z t over r. By our previous reasoning, this quantity ends up scaling like t squared over r squared. However, we're repeating this r times. So by box 4.1 in Nielsen and Schwang, which is, by the way, my favorite box I've ever run into, using this box, what we end up getting is the error from our segments is in order t squared over r. And so this means that if we want error epsilon, we can take r in order t squared over epsilon. So what this means is that for any epsilon greater than 0, we can perform a simulation of e to the negative I in general of a plus b of t using order t squared over epsilon simulations of a and b. Now we can do this recursively. If we have 3 terms, let's say we had a plus b plus c, right? What we can do is we could envision breaking this first up into 2 terms and then breaking up this again. So by repeating this process, we can end up also getting a doing this in general for an arbitrary number of terms. And so this allows us to be able to simulate, in general, sums of particular terms. Now, next time, what we're going to do is we're going to be talking about techniques to be able to improve this scaling, because this says that we can simulate arbitrary dynamics going back to the previous figure, let's see where that is, over here, we could simulate arbitrary dynamics, but the problem is that the time scaling, it really kind of sucks. The time scaling that we need to do this on a quantum computer scales quadratically with the time that we want the system to evolve for. So this means that there's a substantially greater overhead for the quantum computer to evolve in time than there is for the natural system, which takes only time order t. So the question is, how close can we end up getting to this? And I'm going to show you a tactic that will be able to allow us to get very close, within t to the arbitrarily close to linearly in t. Also, I'm going to argue, using a no fast forwarding theorem, that this is actually the optimal scaling that we can possibly get. And that argument is going to follow from a polynomial lower bound on the parity. Because if we could do faster than linear scaling, we'll be able to show that we could actually violate lower bounds for computing the parity of functions. All right, well, thank you very much. I'll see you all next time.